Hello everyone. So, for this week's lab, we'll be going over ANCOVA and MANCOVA. Essentially, ANCOVA and MANCOVA, it's the same as ANOVA and MANOVA, except we have a covariate. That's that C in there. And what that covariate does is we're partitioning out variance that's caused by that covariant. So really, it's just a slightly fancier way of doing an ANOVA, but you're able to control for some other variable that you think might be getting in the way. Our example that we're going to use for this lab is the Mmpi. So those of you that are in clinical psychology are probably learning about the Mmpi right now, or will be very soon. The Mmpi has a number of different scales that are either clinical scales, most of them, but it also has a bunch of validity scales. So these validity scales essentially are telling us, okay, is this person actually telling us the truth in their responses? So L is the lie scale. So they're trying to fake good. K is defensiveness, so they don't want to tell you about bad things. And F is attempting to fake bad, so that's malingering. We also have clinical scales. So the ones we're going to look at for this lab are hypochondriasis, so hypochondriac, having physical complaints that have no basis. Hysteria, which is a term that I still don't quite understand because I'm not a psychoanalytic person, but it is somewhat similar to anxiety. And schizophrenia, so that kind of really measures attention or withdrawal. For this assignment, we're going to conduct a two-way MANCOVA, or ANCOVA, where we look at clinical group by gender across the three clinical scales, testing the assumptions, and testing the assumptions for this by looking at the homogeneity of regression planes and hyperplanes. We're going to also interpret significant findings, and we'll be using the above three validity scales as covariates. Mostly today we're going to be going through the assumptions. We'll go into, I'll probably cover a bit of the assumptions again in lab just because this is a confusing topic, but mostly we'll save the actual interpretation of the tests for lab. Okay, so what we're going to be doing today is the first thing you always need to test is there has to be a correlation between the dependent variable and the covariates. So essentially, there's no point in including things as a covariate if it's not related to your outcome, because that means it's not going to affect your results, really. So let's do that first. Okay, so here we have a correlation table with all of our outcome variables and our covariates. So we want to see, are these three outcome variables related to these three covariates? So I'm just going to look, let's say here. So lie scale, It's not correlated with being a hypochondriac. Hysteria, also not related, and schizophrenia, also not related. So that's telling us that probably the inclusion of the lie scale as a covariate would not make sense. This is a bad covariate. Next, we can look at the F scale. So remember, the F scale is being defensive. So people who scored high on saying that they are hypochondriacs also scored high on defensiveness. They also scored high on the hysteria scale and high on the schizophrenia scale. So that would suggest that the F scale, it's a pretty good covariate to use. The K scale, on the other hand, again, not a significant correlation, and significant. So maybe it could have some impact on the outcome if it's included. For the purpose of this assignment, we're just going to include them all. Okay, so the next thing we need to do is the new thing that's a little weird, and it's going to take a little bit to wrap your minds around. We need to look at the homogeneity of regression slopes, or planes, or hyperplanes. Essentially, we need to see that everything is related in a similar way. Right? That's what homogeneity means. Everything is similar. So homogeneity of regression slopes would mean that, so here we have some examples. If one if the covariate, so say we have one covariate and these three outcome variables. If we have this fairly strong positive relationship with one, as in this first graph, then less, and then even less. So with this last one, the relationship with the last outcome variable being near zero, that might cause a problem because all of this is pooled. Remember, anytime we need homogeneity, it's because everything is being, anytime we need homogeneity, it's because everything is being pooled. So, yeah, essentially, we want the relationship between the covariate and the dependent to be constant across different treatment levels. So here, clinical group and gender are our two independent variables. So if, let's say for clinical group, the first clinical group, let's say for the first clinical group, if it looks like this first graph, and then the next one, it's this last one, well, a strong positive correlation, strong positive relationship, and then barely any of a relationship, then the estimate you're getting from pooling the variance isn't going to be accurate. Now, where do these planes and hyperplanes come in? Well, at that point, it becomes, here we were able to kind of look at what that relationship is in this nice tidy way, because it's just the relationship between two variables. Well, if you add a second covariate in, then that means now you're looking at the relationship between three variables. So both of the covariates together and the outcome at a certain level. And so if we're looking at 3 levels, then that means that it's a plane. So we can, if you think of a 3D box, I have a box on my desk right now. So I'm imagining the slice through it of if I open it at its hinge, that's going to be a plane. It could also be more on an angle. So picture a tarp that's being held up on one end and on the ground on the other. You know, you might see just one end being high and the other sides all kind of touching the ground. That's kind of what a plane is. Does it matter? No, it's okay. You don't need to know it super well, but all you need to know is that it's what's happening when you're trying to think of how three variables are related. Hyperplanes are 4 variables because now you have 3 covariates and your outcome. And that's where it gets fuzzy because we live in a 3-dimensional reality, and so I can't give you an example of what a hyperplane might look like. But, you know, the computer just added an extra dimension in there because the computer doesn't live in our reality. It lives in whatever reality it wants. So don't worry too much about that. It's essentially the same thing. At the end of the day, all of these regression slopes, regression planes, or regression hyperplanes, planes and hyperplanes are just the same thing as these slopes with another variable or two added in. So another dimension added to this graph. How you test for this varies. If you have just one covariate, you can do it in the drop-down menus, the point-and-click menus. If you have more than one, you have to do it in a different way. Let's look at it through the point-and-click menu first. Okay, so in order to test for homogeneity of regression planes, if we were running a simple ANCOVA, so just one outcome variable, and let's say we only had one covariate, we could do that by going into Model, saying we want to build custom terms, and we can move each of the terms over, and then build a custom term that's the interaction between them both. So gender by the L scale. That's added in. Okay, so once we have those terms built, we can go ahead and click paste. Okay, and if I run that syntax, I'll get something that looks like this. So here, just telling me, okay, we have 75 individuals in the women category, 80 in the men. The intercept, again, we don't care about intercept. These are the effect sizes for gender, the lie variable, and gender by lie. Here, we can tell if there's if the assumption has been violated by checking the interaction term in this test of between subjects effects table. So here we can see this outcome variable non-significant. So this is telling us that we have met the assumption that gender, for the outcome variable of gender, the lie scale has homogeneity in its regression planes. So here, this is another example. We could instead check and see if the clinical group testing testing F by clinical group, if the homogeneity of regression planes has been met here. So here we don't have just two categories, we have 4. Again, we want to look at the tests of between subjects' effects. Here we can see that the clinical group by F, well, that's significant, right? So this is telling us that for this group, there's a significant difference between the regression planes between these grouping categories. That the relationship between schizophrenia and hypochondriasis is different. The relationship between these two variables and the F scale is different depending on what group they're in. Now, this doesn't mean that we can't necessarily run it, but you probably shouldn't. It's something that needs to be addressed. Okay, so that example showed you what to do if you have just one covariate. If you have more than one, it becomes a little bit more involved to check if your homogeneity of regression planes and hyperplanes are met. So let's look at an example of where we have two covariates. So in order to test to see if the homogeneity of regression planes has been met or violated, we would use a syntax looking something like this. So this first part of the syntax is just normal. So title, I think it's actually too long for SPSS. It doesn't like it. Then telling you we're doing a MANOVA. These HS, HY, and SC are the normal outcome variables. And then our L and F are the covariates. Gender and clinical group are independent variables. So here we're saying that we want to look at those outcome variables with the covariates. Specifically, if you look at this design section, I separated it out with lines so that we can see each term a bit more clearly. First, we just have the pooling L and F. So we're saying all of the variance that's related to L and F, we put them together. Then we're saying that there's gender. Okay, that's one of our variables in this group. Okay, then we have clinical group. That's another one of the variables. And then again, normal, gender by clinical group. Got to have the interaction term of those two together. Next, what we do is we want to look at, is there an interaction? So what we're doing is simply combining all of those terms together. Now remember, before, all we had to do was pool all we had to do was L by sex. Here, since it's pooled, we would do pooled L and F by sex. And then also pooled L and F by clinical group. And then again, pooled L and F by the interaction of sex and clinical group. So essentially, what we're trying to do is first, we're specifying all of the variables. Then we are building that interaction term. That interaction term is just looking at each of the options put together. So the pooled variance of our covariates times by each of the other terms. We could add in another covariate very easily just by saying pool L, F, and K. And then, voila, we would have homogeneity of regression hyperplanes. Sounds kind of fancy, but at the end of the day, it's not that bad. Okay, so let's look at what this output looks like. Okay, so here it's telling you we have variates, so these are the dependent variables, and covariates, so things that are changing with the dependent variables, and we want to parse out the variance that the covariates are adding. So this design one is just the normal ANCOVA. That's not what we want to look at, not quite yet. So here, we're going to scroll all the way down. Okay, so here we found, okay, design 2. This is the one. We know it's the one because here we're seeing there are no covariates. That's perfect. L and F aren't being used as covariates here. They're being used as interaction terms. So if we pool these by gender, pool these by clinical group, and pool these by the interaction between gender and clinical group, is there an effect? Now let's look. These are the overall Omnibus F tests. So we do not want them to be significant. If they are significant here, that means that we do not want these to be significant. If they are significant here, then that means that, we don't have homogeneity of our regression planes, because that's what this effect is looking for. So we see here, no, we're doing pretty good. And looking at the univariate F tests, this still looks good. So even though we saw that there was potentially a problem if we only had one covariate, once we pooled both of the variances together, overall, things end up looking the same. So it's always important to look at the right tests. Okay. At the end of this document here, we just have the directions. I've been following them. It's just how to run an ANOVA. Sorry, how to run an ANCOVA and a MANCOVA. So overall, pretty similar and simple. We'll go over a little bit how to interpret the actual ANCOVA and MANCOVA in lab. But until then, I encourage you to try to think about or even write up the results of that we found today for the assumptions. So remember, we had two questions. Is there a significant correlation? And do we have homogeneity of regression planes? How would you write this up? And what would you include in that write-up? What stats? What numbers? Think about that, write it down, and come to class with some thoughts. And I will see you all on Monday.